Hello. Today's lecture forms the first part of a mini-series of talks dealing with the topic of uncertainty in reasoning. Part 1 deals with the application of probability theory, specifically Bayes' rule, which is pretty much the only rule you'll need for constructing something called a Bayesian belief network. Part 2, to come later, deals with those Bayesian belief networks and the problems that go along with them. Finally, just at the point when you're starting to curse the idiot who first came up with all this, I introduce two alternatives to probability and Bayes' rule, namely Dempster-Shafer calculus and fuzzy logic. I should warn you that this lecture is going to be very heavy on the maths, almost all maths in fact. If that's a problem, other than sitting this one out, I really don't know what to suggest. Last week we met the concept of an expert system, which took information from the user and came up with conclusions based on it. An artificial intelligence doctor might ask the question, is the patient running an unusually high temperature? And in the simple systems we've looked at up to now, the only possible answers have been yes, no, or I don't know. The program would then have particular strategies for dealing with each of these different outcomes. But I'm no doctor, well, not a medical one anyhow. I don't know what qualifies as unusually high for body temperature, and I don't have a thermometer on me. The best I can do is place my hand against the patient's forehead. Seems a little hot to me. How do I get this information into the expert system? A better designed expert system would have an interface something like this. Same question, but this time you drag a green slider bar between two limits, from no, definitely not, up to yes, definitely. This way you can represent any degree of certainty in your answer, or lack of it, with I really don't know exactly halfway. The result of this question will be represented by a number in between two fixed limits, perhaps in the range 0 to 1, or 0% to 100%, or maybe -1 to +1, with 0 in the middle representing complete ignorance. The problem occurs when we try to derive conclusions by combining observations that are only known to a certain degree. Here's a rule from the AI doctor, which states that if the patient has pale skin, a high temperature and bloodshot eyes, then he is suffering from green river fever. For all you hypochondriacs out there, I should point out that green river fever is a disease that I've just made up. We have a certain belief in all three of these symptoms, but how certain are we that the patient is suffering from green river fever? This is where some sort of calculus is needed to combine those values in some meaningful way. One thing to note is that such an expert system can no longer give a definitive diagnosis of the disease, unless the observer can report with absolute certainty that a particular symptom is present or absent. It can only give a list of possible diagnoses with certainty factors, indicating how confident it is in each diagnosis. If the observer reported that the patient definitely didn't have bloodshot eyes, and that was one of the absolute must-haves for green river fever, then the expert system could rule that one out, of course. But other than that, it could only state that it is X% sure that the patient does or doesn't have a particular disease. This brings us to the main topic of this lecture, the use of probability theory and, specifically, Bayes' rule, to combine and update belief in evidence. This is where the maths starts, and also the notation that looks a bit like Egyptian hieroglyphics. You're going to be hearing the word probability at least 3 times in every sentence as well. If you are already familiar with the basic ideas of probability theory and want to skip ahead to Bayes' rule, move the viewing point of this video to the time shown at the bottom of the screen. Here, letters of the alphabet represent statements that could be true or false, or believed to be true to a certain extent. I've used the letters A, B and so on to represent these statements, so A could represent the patient has bloodshot eyes, and B could be the patient has a high temperature, and so on. All probabilities lie in the range 0 to 1, with 0 representing impossible and 1 representing certain. If you tossed a fair coin, for example, the probability of getting ahead would be half, or 0.5 if you prefer, what we would colloquially refer to as 50-50, which makes sense. We represent the probability of something happening by placing the statement, or the letter representing it, in brackets, preceded by a small letter P. The downward pointing hoop which is sometimes termed cap, indicates and, i.e. the probability of A cap B is the probability that both A and B are true. The upward pointing hoop, sometimes called cup, indicates or, i.e. the probability of A cup B is the probability that either A or B or both are true. The vertical line in those brackets separating two statements indicates the probability that the first element is true given that, or assuming that, the second one is true. We take that second statement as accepted fact for this probability and give the probability of the first statement on the basis of that assumption. For instance, if I picked a person at random from the population of London, the probability that I would have chosen a policeman is very low. However, if I restricted myself only to picking someone who happened to be sitting in the police car at the time, then that probability is considerably higher. What the second probability is the probability that the person is a policeman given that he's sitting in a police car. If you draw a line over the statement in brackets, sometimes called bar, as in A bar, then it means the opposite of A. The probability of A bar is the probability that A is false, or that the opposite of A is true. You get this by subtracting the probability of A from 1, meaning certainty. So that if A is a statement, the weather is sunny, and the probability of A is 0.3, then the probability of A bar is 1 minus 0.3, i.e. 0.7. This is the probability that it isn't sunny, not the probability that it's raining, just the probability that it's not sunny. We get the probability of A and B both being true by multiplying the probability of B with no reference to A, and the probability of A given that B is true, as shown. From reading this, it does look as though A and B are being treated differently, whereas if you think about it, it shouldn't matter which way round you put those two. The probability of A and B both being true is the same as the probability of B and A both being true. So we can write those two letters the other way round in the right-hand side of the formula as well. If A and B are independent, that is to say the truth of A has no bearing on whether B is true or not, and vice versa, then the probability of A given B simply reduces to the probability of A on its own, i.e. B doesn't affect A, so we just remove it from those brackets. In this case, we get the probability of both A and B by multiplying the probability of A and the probability of B. To get the probability that either A or B or both are true, i.e. the probability that at least one of them is, you add the probability of A and the probability of B, and then subtract the probability that they both are true. If A and B are mutually exclusive, i.e. it is impossible for them both to be true, then the probability of both A and B is 0, and we get the probability of either A or B being true by simply adding the probability of A to the probability of B. These two formulae, one for and one for or, are standard and are well worth remembering. There! Aren't you glad that you're not playing some sort of drinking game where you have to neck a shot of alcohol every time I say the word probability? From now on, I'll refer to them as P of A, or P of both A and B, and so on, to streamline things. Meet the Reverend Thomas Bayes, a vicar and mathematician who lived in 18th century England and after whom Bayes' rule is named. Or rather, we think this is a portrait of Bayes. Rather appropriately, there is some doubt about the identity of the person in that picture. Either way, Bayes was interested in the question of how we should update our belief in any hypothesis as we accumulate evidence both for and against it. Being a gambling man, the hypotheses in his case were, I suspect, the chances of any particular horse winning a race, and the evidence that he wanted to account for being weather conditions, the firmness of the racecourse, and so on. His ideas are written up in a paper called An Essay Towards Solving a Problem in the Doctrine of Chances, how they referred to probability theory in those days, which was presented to the Royal Society in 1763 after Bayes' death. Bayes' rule appears in two forms, a simple one and a slightly more complex one. Instead of letters A and B, we will use H to represent some hypothesis, which might or might not be true, and E to represent some evidence that comes in. Before the evidence comes in, we have a certain initial belief in the hypothesis, the probability that it's true. This is P of H. Mathematicians who want to sound pretentious refer to this as the a priori probability, meaning the probability beforehand. Hey, it's Latin, why not? Then the evidence comes in, and again that evidence has a confidence factor. We have a certain belief in it, P of E. This isn't necessarily the degree to which you believe your eyes, but the probability that the evidence could occur completely independently of the hypothesis. For instance, if we're trying to diagnose whether the patient has green river fever, and our evidence is a patient with clearly bloodshot eyes, we still wouldn't say that the P of E was 100% or certainty, as there might be many reasons why his eyes are bloodshot. Maybe there's also an epidemic of conjunctivitis in town, or a particularly virulent form of hay fever that could account for it. So P of E has two elements to it. To what extent can I trust my observations, and to what extent is this evidence a reason to believe the hypothesis? We already know that P of both H and E can be written in two ways. P of H multiplied by P of H assuming E, and P of E multiplied by P of E given H. So we can set those two expressions equal to each other. Just divide both sides by P of E to give the simple version of Bayes' rule in that red box. We now have the probability that the hypothesis is true updated by the new evidence, what those pretentious mathematicians call the a posteriori probability. The good thing is that it's expressed in terms of things which we can probably easily work out, such as how likely it will be that the patient with green river fever would have bloodshot eyes, and how likely bloodshot eyes are in the population at large. I said there was a slightly more complex version of the formula, and we get it by expanding the P of E term in the denominator of that fraction into two separate terms, one assuming the hypothesis is true, and one assuming that it isn't. Between them, these two cover all possibilities. Either that hypothesis is true, or it isn't, and those two things are mutually exclusive, so we can just add those two probabilities. The new expression for P of E is then patched in for the denominator of that fraction. And that gives you the more complex version of Bayes' rule, which mathematicians use to try to impress girls at parties. Little tip here, that doesn't work. Now, even at the other end of the internet, I can feel your eyes glazing over. Time to put a rocket under all this mathematics. You are the sole mathematician on a jury at a murder trial. So far, the prosecution has produced very little evidence of the man's guilt, but then they hit you with their trump card. A hair found at the scene of the crime with a perfect genetic match to the defendant. They call in a forensic expert who testifies that only one person in a million has the same genetic makeup as that hair. Looks like an open and shut case, doesn't it? On the basis of that, is he guilty or not guilty? Well, before the prosecution produced that hair, the evidence against the accused was pretty flimsy. Let's say that the a priori probability of guilt is 0.05, pretty low. What we want is P of H given E, where E is the statement that the hair came from the accused. To get it, we need to calculate various other factors first. Firstly, we know that P of not H is 0.95, as it is 1 minus 0.05. If there's a 1 in 20 chance that the man is guilty, then the chance that he isn't is 19 in 20. Secondly, what is P of E given H? i.e., assuming the defendant is guilty, what is the probability that the hair came from him? Well, if you think he did it, this must be certain, or at least almost certain. Let's call it 0.995, just to be on the safe side. The other unknown is P of E given not H, i.e., how likely is it that a hair matching the defendant will be found at the crime scene if he turned out to be innocent? Well, the forensic scientist said that only one person in a million would match that hair. The only problem is that there are well over 1 million people in the country who could have done it had they been present. Let's assume, given the nature of the murder, that there are 40 million people in the country capable of doing it. That still leaves 39 people out of the entire population who could be the murderer. After all, we have no way of knowing why the police focused on the defendant in the first place. Perhaps he was the only matching person in their genetic database. If they had had the genetic profile of every single member of the population on their computer, they would have had 40 suspects to choose from. But they didn't, so they concentrated on him. P of E given not H is therefore 39 out of 40, or 0.975. Putting all these figures in the formula and cranking the handle gives 0.051 to 3 decimal places. That so-called key evidence barely made any difference to our level of belief that the defendant was guilty. The only correct course of action is to acquit. Why did the evidence make such little impact on the chance that the man is guilty? Because that impressive 1 in a million statistic is the probability of the evidence, not the probability of guilt. It tells us how rare such a genetic match would be in the population. But that is watered down severely given the vast number of possible suspects not considered by the police, simply because they didn't know about them. That's probably enough about Bayes' rule for the time being. I'll bet you're sick to death of it, aren't you? In the next lecture, I'll show how Bayes' rule can be applied to Bayesian belief networks and expert systems in general, so you'll have a lot more mathematics to look forward to. Oh joy! In the meantime, here's a little problem that you might like to consider. You'll get the answer to it in the next lecture. You are the only doctor on an island where there are only 2 diseases, the common cold and galloping lurgy. Both diseases have the same symptoms, runny nose, sore throat, etc., and sufferers of both these diseases are 98% likely to show these symptoms. But galloping lurgy is fatal within a few days. It is quite widespread. Indeed, 1% of the population have had and died from the disease. On the other hand, 20% of the population have the common cold at any point in time. A man comes into your surgery suffering from runny nose and sore throat. After you've examined him, he turns to you and says, "Give it to me straight, Doc. What are my chances?" What do you tell him? And with that, I shall bid you goodbye for the time being. Don't forget to click on the like button, share the video with your friends, especially if they like maths, and subscribe to the channel. You might also like to comment below, perhaps with your answer to this latest medical question.